Hi, everybody. So now we're going to look at one more really important example of a matrix type group, and that's the group of Euclidean symmetries, or which are sometimes called the isometries of Euclidean space. And these are the group of rigid motions of space which don't necessarily fix the origin, but which do preserve the distance between points. So let's make this precise. So the Euclidean group in n dimensions, which is called E sub n of r, is the group of maps from Rn to Rn, functions from Rn to Rn, which preserve distances. And preserving distances mean that for any pair of points x and y, the distance from f of x to f of y, I'll put the square in, is the same as the distance from x to y. And the fancy word for such a map is that it's an isometry, which means comes sort of from the words same distance. And we've seen some examples of isometries. The orthogonal group gave linear transformations that fix the origin and that preserve distances. That was part of the definition. What's new, as we'll see when we allow more general isometries, is that you can include translations. And a translation is just what happens if you shift by a constant. So it's like the map in one dimension, and a translation would be x goes to x plus 5, which shifts everything 5 units in one direction. And more generally, the translation is you have x in Rn, and you add a fixed vector a in Rn to every x, and that's your transformation. And that's not linear because, in particular, if a is not 0, then t of 0 is a. And if it was linear, t of 0 would have to be 0. So that's a natural kind of map to consider. And of course, I think you can see why it preserves distance, because the distance from t of x to t of y is x plus a minus y plus a. And then the a's just cancel. And so it preserves distances. And now we want to take the group we're eventually going to take the group of all such maps, all distance preserving maps. And in order to connect that back to our work with the orthogonal group, we're going to prove the following proposition, which says that if you have an isometry that carries the origin to the origin, then it's given by an orthogonal matrix. It's an orthogonal linear map. So here the key thing is that we're going to assume that f from Rn to Rn is an isometry, so that the distance between f of x and f of y squared is the same as the distance from x to y. And we're going to assume that f of 0 is 0, but we're not assuming that f is linear. Instead, we're going to show that f is linear. And let me just point out that if this is true, then it's also the case that norm of f of x squared is equal to the norm of x squared, because this is just f of x minus f of 0. We're assuming that f of 0 is equal to 0, and so by the property we have it doesn't just preserve distances, but it preserves lengths, which is distances to the origin. So that's just something to keep in mind. And the first thing we're going to show is that not only does it preserve distances, but it also preserves angles. And the way what we're going to show is that that dot products are preserved. And that's because, the reason I say that's like preserving angles, because as you remember, the dot product of two vectors is like their product of their norms times the angle between them, cosine of the angle between them. So this is saying that cosine doesn't change. By preserving distances, f also preserves the cosine of angles between vectors, and so in some sense the angles between the vectors. And to do this, we're going to use the same trick we used with the orthogonal matrices, namely we're going to look at the dot product f of x minus f of y with itself. And we're going to expand this out as f of x dotted with f of x, which is f of x squared minus twice the dot product of f of x with f of y plus the dot product of f of y with itself. But by our hypothesis, this is the same as the dot product of x minus y with itself, which is equal to the dot product of x with itself minus twice x dot y plus y squared. And if these two things are equal, then, and remember that f of x squared is the same as x squared, that means this is equal to this is equal to this, and so these two things must be equal. Now, we need to show that this forces the map to be linear, because we know that if it is linear and it preserves distances, then it's an orthogonal matrix. And to see that it's linear, let's notice that if we take E1 up to En is an orthonormal basis. That's our standard orthonormal basis. So let's call this 2, orthonormal basis. Then so is f of E1 up to f of En. Because of what we just did with the dot product. Namely, we know that f of EI dotted with f of EJ is the same as EI dotted with EJ, which is 1 or 0, depending on whether I equals j or I does not equal j. So our function takes an orthonormal basis to an orthonormal basis. And now let's take an element x, which is a sum of xi, ei. Any vector can be written in this way, and apply f to it. Now, f of x, we don't know that it's linear, so we can't do what we're tempted to do, which is just to take xi f of ei. But we can use the fact that we have an orthonormal basis. And using that orthonormal basis, we can take the dot product of f of x with each element of our orthonormal basis, and that gives us the coefficient in the orthonormal basis for f. If this is, again, one of these linear algebra things, if you don't believe this works, the thing to do is to take f of x minus the sum, I goes from 1 to n, f of x, f of ei, f of ei, and compute its norm. And what you're going to get if you do this is 0, because you're going to get norm f of x squared and then you're going to get this guy, the norm of this squared, but because this is an orthonormal basis, that's going to turn out to be the sum of f of x, f of ei squared. And then you're going to get all the cross terms. And the cross terms are going to give you an f of x dotted with an f of ei, which is just this coefficient. So the two, So if you haven't seen this before, the way to think about it is, if you look at the difference between this vector and this vector, so you look at f of x minus the sum as I goes from 1 to n, f of x, f of ei, f of ei, and you think about its dot product with each element of this orthonormal basis, you always get 0, because what happens is the f of ej here picks out just the coefficient of f of ej, which is f of x, f of ej, and the first coefficient is also the dot product of f of x with f of ej. So whatever this vector is, it's orthogonal to every element of an orthonormal basis. And the only way that can happen is if it's 0. So this, in other words, this has to be 0. So the two sides have to be equal. In any case, the point now that we can use is that we use the fact that our function is an isometry. And we've shown then that these dot products, I equals 1 to n, of f of xi, f of ei, is the same as the dot product of x with ei. And the dot product of x with ei is just xi. And so what we've shown here is that f of the sum of xi ei is the sum of xi f of ei. And that's basically what it means to say that f is linear. And if it's linear and an isometry, that tells us that f is given by an orthogonal matrix, by the work we did in the discussion of orthogonal matrices. Okay, so this tells us what the isometries that fix the origin are like. What about the isometries altogether? Well, any isometry, let's suppose we take an arbitrary isometry and apply it to 0. It's going to send 0 to some point A. So if I make f twiddle be the function which computes f of x and then subtracts a from it, this is still an isometry. And it fixes the origin. And therefore, it has to be of the form f twiddle of x is ax. And if you combine these things, you see that f twiddle of x, which is ax, is f of x minus a. So the original f of x is big AX plus little a. And that's what I've written here. In other words, the way you make a rigid motion of n space is you first rotate by multiplying by an orthogonal matrix, and then translate by adding some constant vector a. And what happens if you do 2 of those moves? Well, you get this group law here, where you multiply in the first component, and you don't just add the second components, but you add the second components kind of mixed together with the a. And the way to see that is just to calculate what happens if I first do bb applied to x, and that's going to be bx plus little b. And then if I do aa to bx plus b, I get a times bx plus b plus a. In other words, it's abx plus ab plus a. And I think the thing to notice about this is that this is not an abelian group, because that should be the case, because, for instance, if I first rotate by 90 degrees and then take one step to the right, I end up one step to the right. But if I first take one step to the right and then rotate by 90 degrees, I end up on one step up. So those two operations don't commute with one another. And that's kind of where this little extra term comes in, this crossing term. It makes sure that that's where the group's non-commutativity comes from. However, the translations are a subgroup and they live in there as the combinations where the first component is the identity matrix, and you can check that 1A, 1B, according to this formula, should be, well, 1 times 1, which is 1, plus 1 times B, which is B plus A. In other words, it's B plus A or A plus B. So the translations are a subgroup of this group. And in fact, they're a normal subgroup. And we can see that. I'm going to do it all at once by using our first isomorphism theorem. Namely, we have a map from E of n to O of n, which sends a pair AA just to the matrix part. And this is a homomorphism, call that F, because F of AA BB is, on the one hand, AB, that's equal to F of AB, and then AB plus A, but then you forget the second component and you get AB, but that's equal to F of AA, F of BB. And so we have, and the kernel of this map are the things that have a 1 in the first component, and those are precisely the translations. So the kernel of F is the translation subgroup. And then we have one of these nice diagrams where the kernel is automatically normal. So T is a kernel, so it's normal. And we have a map to E of n mod T. And we have the original map F. And then by the isomorphism theorem, since this map is onto, you have an isomorphism between the quotient group and the image of the homomorphism. So the orthogonal group is the quotient of the Euclidean group by the translations. If you look at the case of the plane and you ask yourself, what are the motions of the plane? They really come in four kinds. You can take the plane. Oops. Let's try again. You can take the plane and you can translate it. You can rotate it. You can reflect it, which is not an option that my my tool here gives me, but you could put a reflection line here, and you can reflect across that line. Or you can do what's called a glide reflection, which is a combination of a translation and reflection. That is to say, you could move this square down to here and then reflect it across. And those motions give you the basic types of motions of the Euclidean plane. And in plane geometry, we talk about congruence. We say the two regions are congruent if and only if they can be sort of moved one on top of the other. And now we can formalize that. We can say that two regions are congruent if you can find an element of the Euclidean group which moves one to the other. And from this point of view, you can think of Euclidean geometry is the study of properties invariant by the action of the Euclidean group. And in modern mathematics, you tend to think of geometry as studying properties which are invariant under a group action. And here, this is the classic case of Euclidean geometry. And if you think about it, parallelism is one of these properties, because if you have two parallel lines and you do any of these group actions, they stay parallel. Congruence is one of these properties, because if you move two objects are congruent and then you move one of them, they're still congruent. Similarity is one of these properties. If two things are similar and you move them around in the plane by these rigid motions, they remain similar.